everyone, welcome back to another Pre-Calculus 12 video. We're moving on to 6.4 today, which is graphing, and just like in the last section, I'm going to have to split this up into a few videos because there's a lot of stuff to take in. So I think in order to make this digestible, I'm going to give you a little bit at a time. So I'm just going to basically introduce you to the three basic trig graphs. And in this video, I'm not going to give you an assignment. I'm just going to introduce you. You can soak it in. And then in the next one, I'll start to give you more details on it. So here we go. The basic trig functions I'm referring to is, let me do this in a different color, is sine. Well, I don't need to write it all properly. Sine, cosine, and tangent. So we're going to basically look at those three graphs. I'm going to strip everything away and simplify it in a nice, clear, basic form because I feel like that's what we all need right now. So let's start off first with y equals sine of theta. And I'll draw your attention to the important aspects of the graph. So if this is the graph that we are starting with, I could draw like all of the quadrants, but I'm just going to focus on quadrant 1. So this one up here, because that's where most of the action is happening. And then I will show you the general shape. I'm just freestyling this. I considered putting in grids for grid paper, but you know I have trouble staying in the lines. So there we go. That's basically one cycle or one period of our sine theta graph. So there's key things that I want you to pay attention to, and that is here, here, and here. We would have our X-Intercepts or our roots or our zeros. So I think it's helpful to pay attention to where that is happening. So maybe at the side I'm going to show you a horizontal table of values so that we can start to take a look at, I guess instead of x I could say theta up there. That makes sense. That's like our x value. And if you're finding that confusing, I could instead just say sine x and call this x and call this sine x. So that top one would be the x values and sine x would be the y values. So it really doesn't make a difference. X is our unknown here. Usually when we're referring to trig, we would call it theta. If you want to call it x and sine x, it really doesn't make a difference. I could have written theta and sine theta, and that's fine. But basically to start off with, well, let's fill in some of the stuff we just looked at. So how right here, we have that point, 0, 0. That's pretty important. Okay, and then the next one where we have that happening, I could do this graph in terms of degrees, but oftentimes when we're graphing it this way, we want to use radians. So this is like halfway through, that's going to be pi, and a full cycle would happen at 2 pi. Just to remind you, this is like going a full rotation on our unit circle, but we're looking at it like chopped in half. We're looking at the side perspective or view of what's going on here. So again, full rotation would be 2 pi when we're thinking radians. Remember that that's also the same thing as 360 degrees. So in the other one, if our x value is pi, then our y value would be 0. And for the third one, if we went up to 2 pi, the y value would be 0. So that's just me listing off important aspects of our graph, which is a theme that I've been using pretty much throughout the whole course, is, you know, looking for similarities and looking up for patterns that keep reoccurring and show up in a slightly different form. The next part that I'm interested in is this part right here. That's our local maximum. So that's the highest point on our graph, and that's happening at this point where y is equal to 1. So on our graph, if this is at pi, then this point must be pi over 2. So it's helpful to take our sine graph and to sort of look at it in terms of fractions. So if I like chop it down into quarters, that's like a quarter of the way through, if you think about it. Pi over 2, this would be like 2 pi over 2, this would be like 3 pi over 2, and that would be like 4 pi over 2, or 2 pi. So again, I'm trying to get you to think in terms of fractions. So I hope that that's helpful. So when our x value is pi over 2, my y value would be at 1. That's me talking about this point that I just drew with the teal dot. Okay, so similarly, another important or significant aspect of this graph is this local minimum. That's the lowest point that it's hitting. So that happens, again, remember I talked you through how to do the fractions here. Pi over 2, this pink would be pi, or like 2 pi over 2. So this point must be 3 pi over 2 if we do our fractions right. And 2 pi is the same thing as 4 pi over 2. So here at 3 pi over 2, my value would be at -1 for my y value. Okay, so that's basically a very simplified version of what the sine graph looks like. I feel like that's a nice way to introduce you to this and to get you thinking about this. I am going to just briefly tell you this. I only drew one cycle of this graph, but like one cycle or one period. So technically speaking, this graph would just keep going in both directions in that same pattern. So it just keeps going and going in either direction. But I've chosen to just zoom in on one period or one cycle. So I would call this a period. And then the next period would start right here and would go to this point here, where the same pattern starts repeating again. So we're taking a little snapshot of what's actually happening and zooming in on that to take a look at the key aspects or the important aspects of this thing. Okay, then the other thing for us to pay attention to is something called the amplitude. So basically, if I were to take a look at the y values and chop them in half, so a good way to do this is to find the point of symmetry horizontally. In this case, it's no transformations have happened. It's just at this line y equals 0, the graph's being chopped in half if we're looking vertically. So the amplitude would be from the highest point to the midline. So that would be our amplitude. You go from the midline of the graph up to the highest point, or I could have done the other part. I could have done here to here, which also would accomplish the same thing because we're counting it as a distance. So I wouldn't say -1. I would say how far away are those 2 points? And it would be from -1 up to 0. So it's a distance of 1. So the amplitude of this is equal to 1. So your choice, if you want to take the top chunk or top half to figure out the amplitude, you can do that. If you want to take the bottom half, you can do that. But it ultimately means the same thing. And you're basically getting it. I apologize that this is getting messy, but if we want the amplitude, I'm just going to call it amplitude, we could take the maximum value minus the minimum value and divide it by 2. So there's a nice little formula to get the amplitude, but really off of a graph, you can get it just by looking at it the way that I showed you how with those arrows. Okay, I'm just going to tell you about phase shift. Is if we were to take this graph and move it left or right, so that's like a horizontal translation according to the transformations chapter at the start of the year. And vertical displacement would be moving it up or down, which would be like a vertical phase shift from our transformations chapter at the start of the course. We're not going to worry about that till the next video. But for now, I would like for you to basically get a general understanding of what a basic sine x graph looks like. Okay, so now that we've done that, let's do the same thing but with the cosine graph. So let's say we have y equals cosine x, and I'll keep it consistent and do x instead of theta, just because that's what we did for the last one. So maybe what is helpful in the cosine graph is to do the same sort of thing. I'm going to put my focus, like it technically still keeps going. It looks just like the sine graph, but it's shifted over. But I'm going to take this snapshot and just zoom in on one period of it. So basically a cosine graph starts at 1 and goes up like this. So to kind of get you to think, just like in the last one, it actually technically would keep going that way. It would keep going that way, but we're going to just zoom in on that white portion that I've drawn there. And we'll use a similar approach to last time. I don't know what I'm doing here. I don't want that there. I want to do a table of values, so I hope you're okay with this. I'm going to do x here, and I'm going to do cos x here. And we're going to take quite a similar approach to what I did last time. I want to list off some of the significant aspects of this graph. So this time we're going to start with the maximum value. Like last time, that happened later on, right, at pi over 2. This time it's happening right at x equals 0. So when x is 0, my cos x at that point is 1. Okay, and then this time, if we want to get to our, what are these things called? Our x-intercepts, or our zeros, or our roots, whatever you want to call it. This would now happen, well, let me go back to the minimum. Let me keep things consistent. So this minimum would happen at the halfway mark. So we can see that that's the halfway mark. This endpoint would be like 2 pi. So basically, I'm going to take a bit of a break in between here to show you that at pi, when the x value is pi, my minimum value is at -1, which is this point down here. Oh my goodness, I did not mean to do that. Sorry, everybody. Meaning, like, I want to get rid of this green dot I just drew. Okay, good. I did it. So this point here, I meant to say, is going to be at pi, which is at -1. Okay, so you can see what's happening there. That's me shifting, like, if you can sort of make sense of this, that's me cutting the graph in half. And then if I want to look at my x-intercepts, well, if this is pi, then this must be at pi over 2. So when I have an x value of pi over 2, my y value at that point would be at 0, because that's one of the roots. If that's pi over 2, and this would be like 2 pi over 2, then this must be 3 pi over 2. So here, when I have 3 pi over 2, that's also a 0 here. If I were to keep this going, here I could say at 2 pi, maybe I will do that. At 2 pi, I'd be back to this same pattern where my y value at that point would be at 1. So here to here, we usually wouldn't include 2 pi. I would say x is less than or 2 pi. But I just did it so you can see that pattern, but know that this last point is sort of unnecessary. It's talking about that point up there. So I hope that that helps to clear up the difference between the sine x and the cos x graph. Sine x starts at 0, cos x starts at y equals 1. So that's a pretty significant difference to sort of focus on or to look at. And I want to show you it's the same thing that's happening here. This is still one period. But this time the period I chose to start, I like to always start at x equals 0. But you're basically just looking for where the repetition starts again. So this is like the point, this is as far as I can go before my pattern starts to repeat again. That's what one period is. To be precise, or to be I don't know what the word is. I'm having troubles. So at the bottom here, looking at this -1, I could choose that as my starting point for my period, and then I'd look for the next point like there, where it's at -1 again. But that's a little more messy and complicated. I like to start at 0. So it's nice to keep things basic and to go back to a starting point to help get some grounding and figure out where to look at things from and to get some perspective. And then we talked about the amplitude in the last one. So same idea here. I would want to find the midpoint of my y values. You can see in this case it's just at y equals 0. And I'd want to count up to the maximum or to the minimum. In this case, I'll choose that one. So I would say, just like in the last one, my amplitude here is equal to 1. Once we start transforming the graphs, obviously we can stretch it up and even stretch it sideways and all that stuff. So it will change the amplitude and all of this stuff. But we can see what's going on there. Okay, so I hope that that helps to get a sense of what the cosine x graph looks like. And then let's briefly look at y equals tan x. Sine and cosine follow the same type of pattern, right? They're both called sinusoidal graphs. If you look at them, I can shrink it down to compare and contrast the two so you can see it all. You can see the similarities between the two, although I drew cos x way taller, but they're meant to be about the same. But they show a similar pattern. It's just that cos x is like sin x moved over a little bit. And we'll talk about that later on. Tan x, on the other hand, has a whole other thing going on. So when we go to look at tan x, I'm going to show you a similar type of thing, but I'm going to shift it over just a little bit when I go to graph this one out, because I need to go a little bit left into the negatives to help to really drive this point home. The most important or significant thing I would say with tan x is that it has asymptotes. To remind you, asymptotes is a line that the graph gets closer and closer to but doesn't actually ever reach that line. So it approaches that line. And that happens at, I'm going to draw it here, at pi over 2. So I'm just to really make it clear and obvious, I'm going to actually draw in the dotted lines on your graph. Obviously, you wouldn't really have to do that. Negative pi over 2. I'm doing that to visually really make this clear and draw your attention to the important aspects of this graph in an attempt to try to make it a little more clear for you to see. So if you think about this, like I like to look at it this way, that's basically like one period. And the period this time, I should keep it consistent and do it in purple. So I could say that is one period. In the last one, the period was 2 pi, right? So here, maybe I'll write that. The period is 2 pi in both graphs. But for this one, the period is pi, because if I counted like the distance that I'd have if I went from negative pi over 2 to plus pi over 2, it would be pi. So to make sense of this, if I did negative pi over 2 and I added to that 2 pi over 2, because that's the same thing as pi, but as a fraction over 2, then it makes sense that I would get positive pi over 2 as my result. So just to get you to clearly understand like where this is coming from or what a period of pi means. And then some other significant or important aspects when we're looking at this, I'm going to do the same type of thing here as I did before to keep things consistent. If I do x up there, then I'm going to do tan x here. I'm choosing to do x because you're used to seeing the x-axis. I feel like that helps make it more clear than putting theta. But it's your choice. You could put theta. Just know that theta would be like the x-axis when you're graphing it. Okay, this is pretty important. There's a point at our origin, or at 0, 0. I'm going to choose that as my starting point. I know that I drew into the negatives there, but I want to make sure that, I don't know, I just want to start at 0. So I also do want to put in another asymptote here. So if we're at pi over 2, the next time that I would have another asymptote, if I think about it, is, well, I'd have to add 2 pi over 2 to it in order to get to the next one. So you would see that that's why the next time that I have an asymptote, I'm going to put it like, I don't know, maybe there, is at, no, it needs to be further over. Let's say 3 pi over 2 would have another asymptote there. So to get you to wrap your head around this, this is going to look somewhat similar to some of the polynomial graphs that we've looked at. It kind of looks like a cubic, where on this side it's approaching downwards like this. On this side it's approaching upwards like this. Oh, that little kink shouldn't be there. That's just my horrible graphing or drawing skills. On this one, when I have a value of pi over 4 for my x value, I would have a y value of 1. It's kind of hard to see that on here. I'm just going to mark it off there, and I'm going to put a -1 there. But if this is pi over 2, then that would be happening, like pi over 4 would be about halfway in between 0 and pi over 2, if we think about it, right? Because this would be like saying 2 pi over 4. Okay, so same thing would happen on the negative end. If I had negative pi over 4, then I would have a value at -1, just to help you to wrap your head around what's going on here. So then I just want to give you a sense of the general pattern here. So now here, if we were to keep this going at pi over 2, that would be like undefined. That's how I get an asymptote there. So maybe it's helpful if I draw it in like green there. It's undefined, it can't happen. This is where our asymptote is occurring. And then if you're wondering like, oh my gosh, how on earth do I draw a tan graph? Basically, I like to mark down my asymptotes first. I know that my x-intercept or my root is always halfway in between. So I can mark that down, and then I know the pattern it follows. It goes like that on this side and it goes up on that side. And the same thing would happen again over here where it would be coming down here. And if I kept it going, it'd do the same thing on the other side. But I'm running out of room. So you get a sense or an idea of the pattern that a tan graph takes on. This crooked, messy looking thing is the general shape of the tangent graph. So I do want to keep this going so you get a sense of what's happening. At 3 pi over 4, I would have another value at -1. And then if I were to keep that going at pi, I would have a value of 0. So this would be like my pi mark where that's happening. So if you look at it, you know how the period is pi? I could use my x-intercepts to determine that too, because like that's an indication of repeating pattern again. So if I went from there to there, I could also get like, oh yeah, look, there's a period of pi. So this next time over here that happened, it must be at 2 pi. So what I'm wanting you to get from this is the general pattern, and what's important to help to understand that is looking at the key aspects of the graph, like the x-intercept, the asymptotes when you're dealing with a tangent graph, and I've marked off a y value of 1 and -1 just to give us something else to sort of guide us or to get a sense of where it's at. So I think that that's a good place. Well, actually, sorry, before I end this off, if I were to ask about amplitude for this graph, you can see that it's quite different from the previous two. Amplitude was going from the maximum to the midpoint or the minimum to the midpoint. This doesn't have a maximum or a minimum, so it doesn't have an amplitude either. So we would say nothing for the amplitude. And so I hope that that helps to give you a general sense of key aspects of sine, cosine, and tangent graphs.